Good evening and welcome to the Moscow Telecommunication Seminar. Our today's speaker is Evgeny Khorov. Evgeny is head of the Wireless Networks Lab at the Institute for Information Transmission Problems of the Russian Academy of Sciences, head of Telecommunication Systems Lab at Higher School of Economics, and associate professor at Moscow Institute of Physics and Technologies. He has led dozens of national and international projects sponsored by both academic funds and industry. He has authored over 100 articles. He is IEEE senior member and a voting member of IEEE 802.11 working group. He has contributed to the both 802.11ax, also known as Wi-Fi 6 standard, and 802.11be, Wi-Fi 7 standard, and 802.11 real-time applications technical interest group with many proposals. Today, he will tell us about the issues that are still open in Wi-Fi 6 standard. Evgeny, the floor is yours.
Thank you, Vyacheslav, for introduction. Good evening, everyone. So let's start. Last time when I talked about the evolution of Wi-Fi, I mentioned that there are several amendments that are very impactful. Indeed, they increase throughput, and throughput is the KPI which is maybe the most important for all users. If we look only on those amendments that describe operation in traditional 2.4 and 5 GHz, we can see that every new generation increases data rates approximately 10 times. And this was true before Wi-Fi 6. Wi-Fi 6 is an exception. It focuses on efficiency or user output, but not on the nominal data rates. And today we will talk about Wi-Fi 6, which is defined by 802.11ax amendment. And we will see why this technology is so important and what are the open issues in Wi-Fi 6. The standard the amendment that describes Wi-Fi 6 technology was approved quite recently, but there are a lot of papers that study its performance. And moreover, in spite of the standard, although the standard was published this year, there are a lot of devices on the market that already support this, the main features of this standard. But nevertheless, there are a lot of open issues. And so let us discuss them. First of all, today I will introduce the main targets of Wi-Fi 6 and its main features, main novelties. And then we will discuss some of them, maybe the most important, in detail. We will talk about new physical layer. We will talk about OFDMA, which is the revolutionary changes in Wi-Fi philosophy. We will talk about some features for spatial reuse, and finally we will discuss features for power efficiency. So let's start with the targets of Wi-Fi 6 and its main novelties. As I previously said, previous amendments were more focused on nominal data rates rather than on real data rates and user experience. And of course, we can see fantastic figures, but in reality, we cannot achieve that. For example, .11ac access point can transmit in theory 7 gigabit per second, as promised by the standard. But for that, the clients need to support 160 megahertz channels. The channel condition shall allow to have 8 partial streams. the traffic shall be saturated. It means that every user has enough data for transmission. There is no interference, and the access point and the client station are close to each other. Of course, in reality, these conditions are never happen, and so 7 gigabit per second is never observed. So instead of trying to achieve or trying to increase just nominal data rates, we need to care on user experience. In reality, today we see that Wi-Fi technology is widely used, and there are a lot of Wi-Fi networks deployed in homes, in malls, everywhere. And a lot of Wi-Fi devices that operate in the same area. And it means that we have very strong interference between devices. Cisco called interference a silent killer of Wi-Fi networks, of Wi-Fi technology. Why? Because the technology that worked yesterday, today can work somehow, but tomorrow will not work at all because of the increased interference. And that's why the developers of .11ax have put a lot of attention to mitigating this interference and to improving efficiency. So they start their work in May 2013 as high efficiency W1 study group. And they had the following goals. So first of all, they wanted to improve performance in dense deployments. They wanted to improve quality of experience for end users. And of course, since Wi-Fi devices are very often battery supplied, we need to take care on power consumption. And definitely we need to improve overall network efficiency, whatever it means. And they did really extremely huge work, and it was finished at the end of the last year. So today we have this standard .11ax that describes the Wi-Fi 6 technology, and it has a lot of new features. So first of all, we have modified physical layer. Then we have uplink multi-user MIMR. Just as a reminder, in .11ac Wi-Fi 5, we had only downlink MU-MIMR. One of the key feature of .11ax of Wi-Fi 6 is orthogonal frequency division multiple access of DMA, which can be used both in downlink and uplink. There are some modifications for off-channel access. There are a lot of features that enable and improve spatial reuse operation. Definitely, there are many features for power efficiency, and one of the most recent feature is operation in 6 GHz band. It doesn't provide any significant technological novelties, but just support for another very wide band, and this band now is open for Wi-Fi networks in US. It is open in some European countries, so I hope soon it will be open in Russia too. So today we will discuss maybe the most important features, which are colored with red. Unfortunately, we do not have enough time to discuss all of these features, but the most important we will try to touch. So we start with the modified physical layer. The physical layer of .11ax is inherited from .11ac. What was done? They changed the numerology. So they changed how we divide the frequency in subtones. And we will discuss it a bit later. Then they provided a bit, they reduced overhead caused by of the guard interval. One of the novelty is a new modulation scheme, 1024 CAM, that increases data rates. And also another modulation, dual carrier modulation, improves robustness. There are some myths widely repeated in many, especially many early papers on .11ax. They said, for example, that .11ax 4 times increases nominal data rates, or it uses full duplex. These are only myths, and the real nominal data rates are increased just by 37%. And the main source of this increase is new modulation. This new modulation is 1K CAM instead of 256 CAM. And of course, this value is 4 times higher than this value, but with 1K CAM, we can transmit only 10 bits per symbol instead of 8 bits per symbol. So the increase is just to 25%. And also there is some small increase because of shortened guard interval. So what about numerology of .11ax5? So the OVDM symbol in .11ax is 4 times longer than .11ac, but the gap between tones is 4 times smaller. So we have this 4 times scaling of .11ac file, which is fruitful for OVDMA, and it is also fruitful for outdoor operation. And because of such longer OVDM symbols, we can have we can have the same guard interval, but the overhead induced by this guard interval becomes smaller. So let's go to OVDMA. So as I previously said, OVDMA is the main novelty of .11ax, and OVDMA allows transmission to several stars in downlink and uplink. To several stations. In .11ax, in contrast to LTE, with its rigid OVDMA structure, in .11ax, OVDMA is used as the per packet basis. It means that a transmitter needs to access the channel, start transmitting a packet, and then this packet has some preamble, which is common preamble, and it's sent for all users. But then various parts of this packet, various parts in frequency domain of this packet are destined for different users. In the common preamble, we have allocation map that shows how various resource units are mapped to users. So what are the modulation coding scheme used for in each resource unit, and so far. In similar way, uplink transmission is organized. But here we have the common preamble, which is transmitted by all stations that transmit in uplink. And to synchronize, we need to provide information to the stations before this uplink transmission, information of what modulation coding scheme shall be used, what will be the duration of this transmission. So all transmission parameters shall be provided in advance. The important feature of DMA in Wi-Fi is that all transmission starts and ends in the same time, and such alignment can be achieved with padding. And for uplink multi-user of DMA, the access point shall receive signal from different stations at almost the same power level. This is important for the receiver. Here you can see several examples of DMA transmissions. So, for example, such transmission can start in downlink. The transmission can start with a multi-user variant of RTS frame. As a response, the stations send CTSs, but these CTS frames are sent in every 20 MHz channel, where that covers the appropriate resource units. For example, here we see that in this 20 MHz channel, two stations are assigned for this 20 MHz channel, so both stations send CTS frames, and these frames are absolutely the same frame. This is very important because when the stations send absolutely the same frame, no collision occurs in the channel. And finally, after this downlink transmission, we have uplink transmission. And in uplink, stations can transmit, for example, acknowledgement frames. In another version, so if we consider uplink data transmission, so it starts with a trigger frame, which defines resource units and all the transmission parameters for the following uplink transmission. And to acknowledge this multi-user transmission, the access point can send a multi-stub locac frame. So this is how OFDMA is organized in .11ax networks. There are some peculiarities. First of all, we have a rather non-trivial structure of resource units, which is shown on this slide. And I see some question in the chat. How does the access point understand from the CTS which star send it? Actually, it cannot understand. So if we receive such a CTS frame, we does not know whether station 2 or station 3 transmit this frame, or both of them transmitted this frame. So the access point assumes that both. So if this CTS is received, the access point assumes that both station replies, and then it sends the data. If one of these stations did not send CTS, so it just does not reply with an acknowledgement, and that's all. So if we allocate less than 20 megahertz band, we cannot understand. In case of RTS CTS, we cannot understand who exactly sent a CTS frame. Again, so why we do not have a collision of these frames? Because these frames are generated by different stations, but the signal is absolutely the same. So you can just assume that we have the same signal transmitted from two antennas. Even scrambler is initialized with the same value, which is given in the trigger frame in this MU RTS. Also, it's very important that the start of these frames shall be perfectly aligned, and that's why .11ax imposes restriction on the accuracy of the timers at the stations, because all these transmissions shall start and end simultaneously. Yeah, and we have done some experiments related to sending these two CTS frames with by different stations, and indeed, if the beginning of these frames is and the end of these frames are synchronized, the frames are correctly received. If we have some shift between the beginning of the frames, we have issues with the reception of the CTS frames. So let me continue with the structure of resource units. The standard defines a very interesting structure of resource units. So consider a 40 MHz channel. So it can be split into 2 resource units. Each of them can be then split into 3 resource units. 2 of them has 106 pilots, and 1 of them has only 26 pilots. Then each of these wide resource units can be split again into 2 resource units, and each of these resource units can be split again into 2 resource units of 26 tones. So every 20 megahertz corresponds to 9 resource units of 26 tones. And wide resource units like 106 pilots and wider can be used with multi-user mimer. In the whole 20 megahertz band or wider resource units, we can use 1 kHz modulation. So every resource unit can be assigned to 1 or several stations. For example, this resource unit can be assigned to 2 stations, which are and transmissions are distinguished with the MU-MIMO technology. But any station can be assigned only 1 resource unit. So, for example, the allocation as shown on this slide, like station 1 has this resource unit, station 2 is assigned this resource unit, and so on so far. So it's possible. This allocation is possible. But such an allocation is impossible, is forbidden. Here you can see that 2 resource units are assigned for 1 station. Every station can obtain not more than 1 resource unit. So OFDMA has a lot of benefits. One of the benefits is that we can increase power spectral density in uplink transmission. For example, if we have only 1 station that transmits in uplink, the station transmits with some energy, with some power, and we have some noise in the channel, and we have such an SNR, signal-to-noise ratio. If we use not the whole band, but only some narrow resource unit, and emit the same power, we can increase power spectral density. Of course, if we have only 1 transmitter, it cannot provide any gain. But if we have multiple stations that can transmit simultaneously, the overall power injected in the channel is higher. And that's why we have a high SNR at the receiver. And in total, we can transmit much more data. Such an effect significantly modifies the scheduling problem. For example, if we consider the very classical and well-known problem of the scheduling problem of minimization of delivery time, it is well known that if we if the channel is if the channel quality is the same, so we need to we need to allocate. We need to start with the station that requires the minimal time to deliver its data, and if you do so, the average delivery time will be the minimum one. But in case of DMA, for example, if we use not TDMA but FDMA, so we start all transmissions in the same time and end transmission at the same time. Every station requires the same time for delivery of data, and the total time or the average time will be higher. But taking into account the peculiarity which I showed before, we understand that with increased power spectral density, we can transmit data faster, and such a solution is better than this solution. Taking into account this effect, we can develop our own scheduler, which minimizes average upload time. And with OVDMA, we can achieve as much as 3 times increase in, 3 times reduce in 3 times reduction in average upload time. Of course, since OVDMA is a much better than legacy CSMA for uplink transmission, the station shall avoid contending for the channel if the access point provides them with the channel resources. So if the channel allocates them channel resources. For that, the access point can send a special information element called multi-user DCA parameter set that defines larger AFSEN and CW mean values for .11 AX stations, and these values say define the probability with which the station content for the channel, each station contents for the channel. The larger are these values, the low is the probability that the station will contents for the channel. So we can, with this information element, we can avoid CSMA, CA at all, legacy channel access at all in .11ax networks. But nevertheless, so we need to somehow indicate that station requires some resources. If the station has no traffic, the access point will allocate no resource unit for the station. But sooner or later, some traffic comes, and we need to indicate that we have some data to transmit in uplink. What can we do if we are forbidden to access the channel with CSMA because of such parameters? And the solution for this is OVDMA random access. Yeah, so what can we do? So trigger frame, the access point allocates some resource units, not for a particular station, but for any stations that has data and that are not allocated any dedicated resource units. And following a special random access procedure, such stations can transmit data in these resource units allocated for random access. The procedure is based on binary exponential backoff as usual. Such an approach performs similar to multi-channel Aloha. And can you imagine there are so many papers that try to improve this random access? Yeah, because it's very interesting academic problem. We have random access, how we can improve it. Do you know what is the best solution for multi-channel slotted Aloha? Here is a hint that Aloha typically shows lower performance than CSMA. And the solution is to avoid usage of random access for data transmission and use random access just to send buffer status reports or some management frames. So we do not have such a problem of throughput optimization for random access at all. because instead of the usage of this random access, we need to use it only for only to transmit buffer status report, and then to allocate some resources, some dedicated resources with the trigger frame for particular stations that have data. Of course, there is still some optimization problems which is related to delays. But delays again shall be considered not for the case when we have a lot of stations that transmit a huge amount of data, but for the case when we have stations that need to transmit buffer status reports. And that's all. I mentioned that OFDMA provides gains in uplink, and these gains are really very obvious. But what happens in downlink? And this is still an open question, and I didn't find any good answer to this question in some papers, in spite of there are although there are a lot of papers that try to improve OFDMA in downlink, in uplink. So there is no good answer for the question of when and how downlink OFDMA can provide gains. Obviously, OFDMA can, with the usage of OFDMA, we can reduce overhead for short packets, but we will see some notable gains only if we have a lot of users that simultaneously try to transmit very short packets. Is this scenario relevant for Wi-Fi networks? It's a question. Definitely, OFDMA can benefit from frequency selective fading, but to have some notable gains, we need that all the stations regularly report very accurate channel quality information. And here we have a trade-off, because to transmit such channel quality information, we need some resources. And it's a question whether the gain of the usage of this accurate channel quality information will be higher than the overhead induced by sending this channel quality information. Moreover, we see that Wi-Fi networks operate in really very wide bands. .11ax in .11x up to 160 megahertz, and the gains provided by frequency selective fading can be observed only for very narrow resource units, but not for the wide resource units. So we need to have a lot of devices that simultaneously transmit. Also, there is a problem that we need to design a very low complexity scheduler. And in contrast to LTE or 5G networks, we don't have regular timing. So some decisions shall be done within TXP. Once we win TXP or win the contention for the channel, the access point needs to decide whom and how it transmit data. And the optimization problem has a lot of constraints, and it's really a multidimensional optimization problem, because in addition to selecting the best resource unit, we need to define which MCS shall be used, whether we need to use MU MIMR, and so far. So there are a lot of dimensions, there are a lot of constraints, but the solutions needs to be done very quickly, and we need a low complexity scheduler. And unfortunately, the problem of finding such scheduler is still open. Now let's switch to the third item, which is improvements for dense deployments. As I previously said, dense deployments and interference are really very important, very crucial for Wi-Fi networks, and interference is a silent killer, so we need to deal with it. In Wi-Fi networks, for example, in .11 AC networks, the main channel in which the network operates is 20 megahertz. But at the same time, the stations can use wider channels if they are idle when they want to transmit. And the standard defines a structure of the channels. Like we have 20 megahertz primary channels in which we try to sense the channel and content for the channel. Then we have secondary 20 megahertz channel, which together form 40 megahertz channel. Then we have 40 megahertz, 80 megahertz channel, and 160 megahertz channel. And once, so Bykov countdown is performed based on the state in the primary 20 megahertz channel. But then we can use wider channel for transmission if the channels were idle, if the corresponding secondary channels are idle. So we consider one by one these secondary channels, and if they're idle, we add them to the primary channel. So it means that if we win the contention in this channel and secondary 20 is idle, we add it and transmit in 40 megahertz. If secondary 40 is idle, we transmit in 80 megahertz, and so on so far. And if, for example, this 20 megahertz secondary channel is busy, but these two channels are idle, we cannot transmit in 40, in 80, in 160 megahertz at all. We can only transmit in 20 megahertz. And this is a very huge drawback of .11ac. .11ax introduced a preamble function procedure, which allows us to exclude some 20 megahertz channels which are busy, and for example, transmit in 60 megahertz if this 20 megahertz channel is busy. So we can just exclude some 20 megahertz channels from the consideration. And this preamble function procedure is rather very flexible, although it doesn't cover all the possible situations. It significantly improves performance if we have dense deployments of the access points which operate in the same 160 megahertz channel, but different 20 megahertz primary channels. Apart from that, the .11ax widely uses network color, which is a pseudo-unique ID of the network, and it is indicated in physical headers of all packets. This idea of the network is very important because since it is located in the file header, it is obtained before and without the whole packet being fully received and decoded. So when the packet only starts, we already know in which network this packet is sent. That's why we can distinguish between inter-BSS and inter-BSS transmissions. And we can implement different mechanism for virtual carrier sense, they're called NAV, for inter-BSS and inter-BSS transmissions. And sometimes we can ignore inter-BSS transmissions. How? Let's see. .11ax introduces the adjustment of sensitivity threshold and transmit power. Just a reminder, Wi-Fi uses carrier sense multiple access, and we can start a transmission only if the channel is idle. What does it mean if the channel is idle? It means that the signal strength in the channel is below some threshold. And by default, this threshold is minus 82 dBm. And this is quite a low value. And it means that even if we have another Wi-Fi network, which is rather far from our device, but the signal from this network is upper 82 is above minus 82 dBm, we consider the channel as busy and we do not start our own transmission. At the same time, what we can do, we can ignore this signal and consider the channel as idle, but at the same time, we can reduce the power of our own transmission. And virtually, it results in separating two networks. So virtually, the distance between these two networks become wider. And if we ignore the signal from another network, we transmit with a smaller power, and our impact on the other network is the same as if we are located at a larger distance. In theory, or in this picture, you can see that the gain should be very high from this procedure. But when we did some experiments, we found that the gain is not so high. Although there were really very huge debates in H2.11ax related to this procedure, and there are a lot of mechanisms which implement this idea. So actually, the gain is not so high as expected. We see that the main gain is again related not to throughput. We cannot significantly increase the throughput, but what we can improve delays if the network is overloaded. Only in this case we can obtain some gains, but otherwise we do not see the gains. Moreover, there are a lot of papers that study such mechanism. It is called SSPD or dynamic sensitivity threshold. So there are several variants of this mechanism. But many of these papers, so maybe almost all papers that I found in the literature, they oversimplify the behavior of Wi-Fi networks or simplified behavior of Wi-Fi networks. For example, they do not take into account the algorithm, rate control algorithm. So the algorithm that defines which modulation coding scheme is chosen for transmission. And in reality, this algorithm has a very strong impact. And in our lab, we have done such research, and Alexander Krotov has done wonderful research that he took into account all the peculiarities and very accurately analyzed what happened in the network. And what he obtained is that if we do not take into account, for example, rate control algorithm, the performance can be even worse because of this mechanism. But if we take into account all the peculiarities and accurately analyze when and how we need to modify these thresholds, so we can obtain high gains in terms of delays. For example, you can see this curve with respect to like this curve, blue curve. But for that, the load shall be very high. So the network shall be almost saturated. We can achieve even higher gains if we provide coordination between the access points. And here we have designed some algorithms, and again, Alexander Krotov is the main contributor for that. And the gain can be really very high, but we see high gains in theory, but the issues are related to how to implement these solutions in real networks if we take into account that the access points work almost independently. Fortunately, in .11be or Wi-Fi 7, one of the direction is to improve coordination and cooperation between access points. And it seems that some of these methods will be possible with Wi-Fi 7. And with such a cooperation, the gain will be really very high, in contrast to what we see in .11ax. AX. And the last item is related to power saving enhancements. So as for power saving, so we have a lot of some small improvements. Small means that we had some algorithm, we have some approach, and with .11ax we improve this approach. But one of the solutions is really very important, and it is important not only from the power saving point of view, but also from but also from the point of view of future Wi-Fi standards that will be after Wi-Fi 6. And it is TWT, or target wake time. This mechanism was originally introduced in .11ah, Wi-Fi Hello, Wi-Fi for the Internet of Things. But Wi-Fi Hello doesn't have huge value on the market. But the mechanism which was designed for in .11ah was pushed to .11ax, and it's really very powerful and very flexible tool to reduce power consumption. Let me describe this this feature. So typically, all power management techniques in Wi-Fi networks are based on the following idea. So from time to time, the device can switch off its radio. But even when the device is in power safe mode and try to switch off its radio whenever it's possible, it needs to receive beacons. Beacons are regular management frames which are sent by the access point, and they provide some management information about the network operation. And if the device transmits very rarely, it spends a small amount of energy for data transmission, but it consumes a lot of energy for receiving all these beacons. And TWT allows devices to allocate some channel times when the device will be awake, and the remaining time the device can be in the down state, so it will not spend any energy. And TWT allows the device to skip the beacons. So beacons are not necessary to be received anymore. So with this mechanism, the devices can schedule a series of channel times called TWT, target wake times, and they can be scheduled in a periodic manner. And at the very beginning, so devices, for example, a station and the access point can negotiate this schedule. So what is the wake interval? What is the duration of each awakened state? Who starts the transmission when a station awakes, and so far. So many parameters. And because of this mechanism, we can significantly reduce power consumption. Together with other .11ax features, TWT provides a very flexible, very powerful framework for power management and power consumption optimization. Because, for example, we can introduce, use so-called opportunistic power save, which is defined in the standard, and combine together TWT and trigger frames. For example, the access point defines some times when the station needs to be awake, and during these times it says whether the station will be served during the next period or not. So it sends whether the access point will send some trigger frames for the stations or not, and it simplifies the scheduler procedure and makes it more flexible. However, we have many issues related to TWT. One of them is clock drifting. So we do not have very accurate clocks on the stations, and if the station is dosed for a long time, the clock drifting effect may result in some missynchronization of the schedules of the access point and the stations. When the station wakes up after a long sleep, it has zero knowledge about the channel state, whether we have some, whether the channel is virtually busy or not. Finally, we always have a trade-off between low power consumption, which requires rather long dose states, and low latency communication, which requires to be awake quite often, because we may have data not only for uplink transmission but also for downlink. And if the station has radio switched off, we cannot transmit anything in downlink. So there are still many issues related to the usage of TWT for reducing power management, for reducing power consumption. So I have described the main features of .11ax. The main, as you see, the main features are related to ODMA operations, spatial reuse, and power management. And instead of conclusion, I would like to say the following remarks. So first of all, in spite of we have a lot of devices that are already of the market, and they're right that they support. So on these devices, you can see some marks saying that they support Wi-Fi 6, so they support .11ax separation. There are still many issues. And support of DMA, trigger frames, and all other stuff doesn't mean that the stations, or the access points really generate these trigger frames and do some scheduling. And it also doesn't say that they do it in an optimal way. There are still a lot of issues related to .11ax optimal operation. So first of all, these issues are related to efficient OFDMA operation, because OFDMA is used in cellular networks for many years, but in Wi-Fi networks it's a new feature, and in Wi-Fi networks it has its own peculiarities, and it's not clear how to really use OFDMA in a very efficient way. We have many issues related to spatial reuse operation. Definitely, spatial reuse will be improved in Wi-Fi 7, but still in Wi-Fi 6, we have some methods that can provide some gains, but how to use these methods in the best way is still unclear. And we have also open issues related to low power delay sensitive communications. Because here we have a trade-off between the power consumption and delays. Some protocol limitations, some issues will be addressed in Wi-Fi 7. For example, I mentioned that in Wi-Fi 6 we have rather rigid hierarchical structure of resource units, and in the Wi-Fi 7 it will be much more flexible. For example, it will be possible to combine several RUs together, and also it is discussed whether how to use OFDMA for direct link operations, so to transmit data between one station and another station without an access point between them. So access point is, but it doesn't participate in data transmission. Also, in Wi-Fi 7, there will be multi-IP cooperation, coordinated spatial reuse, coordinated OFDMA, coordinated distributed MIME, and so far. So all these issues are all these features are discussed now, but some of them, especially the first two It seems that they will be a part of Wi-Fi 7. And of course, these methods will provide more gain, but we still need to do a lot of research to use these methods in the best way. And interestingly, that TWT that was originally designed to allow stations to sleep for a long time and to improve power consumption, Wi-Fi 7 will be used for real-time applications, to support real-time applications. And this is quite interesting because a mechanism which was initially designed to absolutely another problem, moreover, it can be like a contradictive problem, opposite problem, yeah. So now will be used for real-time applications. And what is also interesting from the experience of Wi-Fi 6 is that high data rates are still needed. And if a customer customer wants to buy a new device, it will see what is written on the box. If it is if the customer already has a device that supports 7 gigabit per second, it will hardly, he or she will hardly pay $100 more to buy a device that supports 10 gigabit per second. But it definitely can pay more for larger nominal data rates, even if this customer will never use these high data rates. So high data rates are very important from a marketing point of view. So that's all. I had answered some questions. If you have some more questions, please feel free to ask them. And I see one question in the chat. What is the difference between HCCA, MCCA, and TWT? It seems that the idea of both is to provide periodic channel reservations. Yeah, the frame from mathematical point of view, the mechanisms are quite similar. All of these mechanisms allow doing some scheduling. HCCA is dead because this is a very heavy mechanism. It requires a lot of so it has a lot of drawbacks, and it requires a lot of information about the traffic. So it is not used, as far as I know, it is not used in the devices. Similar for MCCA. TWT, in contrast, doesn't require all this information, and it can be considered as a lightweight mechanism, lightweight approach for scheduling. Another difference between, for example, HCCA, MCCA, and TWT is that the first two mechanisms they try to forbid a channel access for other stations, but TWT does not. So TWT requires additional protection for transmission, and there are some ways how to do this. Any other questions?
May I ask you the question that is more the practical side of the technology? In particular, I'm curious about the chips that will support Wi-Fi 6. Are they already on the market, or anything is in the pipeline?
The chips that support .11ax or Wi-Fi 6 are on the market for many years. So here you can see the first.
Yeah. So that a number of equipment.
Yeah, you can buy it. But again, so what means that they support .11ax? So I talked to some.
That's the major question. Yeah.
Yeah, so they definitely support signaling. So they understand if you send them a trigger frame, they will understand this trigger frame. But whether they send trigger frames by themselves, whether they do of DMA, how they allocate resources is a question. And so since we are participating in the development process of the 11AX, we talked to some vendors, and so these chips appeared when, as far as I remember, the first or the second draft was published. So
Right. Yeah.
It was in the really in the very beginning. So I talked to them and I asked them, so okay, your company announced that you have some chip that support the 11AX. How did you solve this or that problem? They say, okay, what means support? It means that we support frames. And if somebody else send us some frame, we will understand, we will reply on this frame with, we'll process this frame correctly.
Right.
If somebody send us an DMA transmission, we will receive correctly our part of this transmission. But it doesn't mean that we will send our own DMA transmission if you're talking about access point.
Right. Yeah.
So this is a question, and if we compare, if we compare just .11ax and .11ac without all these novelties related to DMA and spatial reuse operation, we see that the nominal data rates are increased just by 37%, and it's hardly worth to buy new devices just because of higher data rates. So I would wait maybe for some time till we have advanced algorithms implemented in this equipment.
When do you expect that?
You see, the standard was published quite recently.
Yeah.
So I would say that maybe some algorithms have been developed for 1 or 2 years. So maybe we need to wait 1 or 2 years more till they be able.
Yeah, that was basically my question. That I know that equipment is out for many years, but the functionality that is implemented there is not like obviously full Wi-Fi 6 or AX, whatever you call it. Yeah. So basically, we didn't find any kind of promising information currently on the market. So, well, they again promise AX, but to get the full understanding what you are buying, you need to buy that and test that.
Sure.
Yeah. Okay. Thank you.
Thank you. And similar question: what does .11x work? How does .11x work in today's APs? What schedulers are used? Actually, I don't know. We were very close to have a project on study on evaluating various devices, but for some reason this project did not begin, and that's why. So I cannot say what exactly is implemented, how exactly the modern device work, because it's rather difficult and it's rather very expensive to do all these experiments and to do, say, reverse engineering, trying to understand what exactly happened with the devices. But this is a very interesting project, and if we had enough resources, I would definitely start this project. Another question about domain, Artyom, could you?
The question is about these two mechanisms can be used together, so we can schedule different users in different resource units, or we can combine them by using multi-user MIME. So what's your opinion in which of the mechanisms provide the most benefit in terms of spectral efficiency or some other criteria, and whether one of them is more important than another, or they should be combined somehow? So maybe you can comment something more about this.
Okay, so I tried, during my talk, I tried to skip all the issues related to MU-MIME for several reasons. One of the reasons is that MU-MIME is quite similar to what was in .11ac. The only knowledge is that now it is allowed not only in downlink but also in uplink, and this is done. This uplink MU-MIME was enabled just because we had this. Now you have these trigger frames and the frame, all the stuff related to the trigger frames, so we can do synchronized uplink transmissions. But the usage of MU-MIME itself is quite a challenging problem, but it's not related only to Wi-Fi 6. And if we compare OFDMA and MU-MIME, so I would say that first of all, we need to understand where and when, in which scenarios OFDMA itself provides some gains with respect to legacy transmission. And here we see some issues, because for uplink it's more or less clear. We have higher power spectral density and we can do it. In downlink, the situation is not so obvious. Of course, if we have significantly different channel conditions in different bands, we can use OFDMA. But if we take into account that in Wi-Fi we have a lot of randomness, and we do not know how long there will be some transmissions, some transmission in neighborhood network, and what is the impact of this transmission on a particular device. So obtaining all this information is too difficult, and it's too heavy, and it's again an open issue, an open question whether we can provide some, whether can have some gain because of these different interference conditions. So I would say that first of all, we need to start with maybe better understanding of DMA itself in Wi-Fi networks, because the effects are completely different to what we have in the LTE network, in cellular networks. And then we will have an answer to your question. Have I answered?
Yeah, thank you. This is, I understand this is a really interesting and still open research question. So just maybe to open a discussion about this problem. So just thank you very much for your comments and answer.
Any other questions? I see and I hear no more questions. Oh.
I can ask another question. If, so the question is about the coordinated power management and these things. So as far as I understand, Wi-Fi 6 allows this coordinated operation only if access points can exchange this information by wires. So they should be connected to some controller, or should have an opportunity to send frames between each other. And is it true, or it also has an opportunity to send by some wireless frames to do this coordination?
So first of all, I would say that we almost do not have coordination in Wi-Fi 6. So this is for Wi-Fi 7. This slide was for Wi-Fi 7, like future work, this one. In Wi-Fi 6, we can group together access points in so-called spatial reuse groups, and then we can implement. We can use a mechanism similar to this one to simultaneously tune off stability thresholds and transmit power. But we cannot coordinate the schedule. So in reality, we can do it. So the standard does not forbid doing this, but it does not provide any mechanism to do it in a standardized way. So the only thing that can be done is use the usage of some vendor-specific protocols or using some management access point management infrastructure and coordinate schedules or coordinate transmissions only in the networks which are deployed by the same vendors. So something like this. What will be in Wi-Fi 7? It seems that there will be some mechanism to synchronize schedule by wireless. So this method should be standardized, and this methods will allow to synchronize schedule by wireless, the schedule of different access points. Yeah. As for distributed environment, so these methods require much more synchronization, and these methods are much more difficult in implementation. So although there is some discussion in the group, I do not believe that there will be some good solutions in the standard for these approaches. But as for coordinated OVDMA or coordinated spatial use, I think they will be a part of this. They will be parts of the standard. Yeah.
So just to clarify, so Wi-Fi 6 does not allow to send this control in 4x wireless frames, while Wi-Fi 7 is thinking on how to implement this, right?
I would say that Wi-Fi 6 allows to do some very very simple coordination, like the access points may belong to the same spatial reuse group, and because of this, they will process some frames in a special way. But this operation is really very simple, and I would not call it coordination. It's just a sort of very simple coordination. But what we often call coordination, like we have some schedule, and the schedule is done in a centralized manner or in a coordinated manner. So I think this will be possible in Wi-Fi 7 only.
Yeah, thank you for your comments.
Thank you. Any other questions?
Yeah, one question from me. As I understand, all the solutions you mentioned are implemented at the access points. Am I right? We need to implement all these solutions at the access points, and we do not need to implement some solutions or some part of the solution at the stations. If there is some solutions that need some modifications in stations, or from the station side, we just need some simple station which supports standard, and we need only some complicated access point.
Actually, a very good question. Thank you. It raises a very important problem of Wi-Fi 6 networks. So first of all the stuff like support of the protocol, support of OVDMA, support of trigger frame, support of spatial reuse, and so on. So far, all these features need to be implemented on both sides, access points and client stations. Because if the access point sends some of the main transmission and the station cannot understand it, so what will be? So they need to be supported. All this stuff need to be supported by both parties. But why I like your question, because .11ax changes the paradigm of how Wi-Fi networks operate. So previously, all the devices were independent. They independently obtain channel access. They independently make some decisions on what modulation coding schemes need to be used, what power to use, and so far. All transmission parameters were selected by the transmitting devices itself. And .11ax changes this paradigm. Why? Because now the access point decides who, which parameters shall be used not only for downlink transmission, but also for uplink transmission. It makes the schedule both for downlink and uplink. It determines the modulation coding scheme both for downlink and uplink. And endpoint devices can be rather stupid in terms of making some decisions, because they will transmit where the access point says. They will transmit with the modulation coding schemes which is provided by the access point. They will transmit with the power given by the access point, and so far. So the devices become more stupid, and all sophisticated algorithms are now operate only at the access point. So that's why all these algorithms like scheduling and some other algorithms need to be implemented on the access point, not at the endpoint devices. Did I understand your question correctly?
Yeah, thank you.
Any other questions? So thank you very much.
Thank you, Evgeny, for your presentation. So the next seminar will be held next week at the same time. It will be devoted to wireless sensor networks. In particular, Dmitry Bankov will present us his talk entitled MCS allocation in heterogeneous LoRaWAN networks. So we will wait for you.
Thank you. Have a nice evening.
Thank you
Goodbye.
too. Bye.
Thank you.